Okay, everyone, now we're on to day 8, which is tangents. All right. First thing, the first couple days of this unit was formulas, theorems. Now what we're going to turn our attention to is different parts of a circle. You guys already know the chords, the diameters, the radii. Now we're going to go into some other special types of segments and lines in a circle. Today, the first special type of line is called a tangent line in a circle. And the definition right here says exactly what I need to say. And that's it. It's a line that intersects the circle one spot only. Okay, one spot only. So you'll notice in the first diagram right here, 3 tangent lines. Okay, again, because you'll see they intersect the circle at only one spot. So this one intersects at B, this one intersects at C, and this one intersects at F. All right, so those are all called tangent lines. All right, tangent lines. Now, why are, in my second diagram, none of these are tangents? Well, it's PQ, intersects twice. RS doesn't intersect at all. TU, well, it does intersect, you're right, but it's got to be a line. And if I keep extending this out, it would intersect in 2 spots. Plus, it's called a radius, right? And then WV, well, that only intersects in 1 spot. So what's the problem? It's got to be a line that intersects the circle in exactly 1 spot, okay? Which none of these do. All right, so tangent intersects the circle, 1 spot only. We can have what's called common tangents. All right, common tangents, which are 2 lines or any lines that intersect each circle in exactly 1 spot. So you'll see my 2 interlocking circles here in this first example. I am claiming that these circles have 2 common tangents, meaning I could draw 2 lines that intersect each circle in exactly 1 point. So I'll give you a little startup here. Here is my first line right there. Okay, there's my first line. Can you draw in the second one? Because I'm claiming there's 2. So I just drew the first one right there. Intersects the circle and each circle in 1 spot. And then some of you are probably already guessing, and you're correct. Right down below here is my other common tangent. Okay? Oops. All right, so there's the second one right here. Okay. All right, next one. I'm claiming they have 4 common tangents. 4. You draw them in. I'll pause the video. Okay, take a look. Did you get all 4? All right, would have loved to have my straight edge there, but did you get all 4? All right, we'll see. All right, but that's where all 4 are. All 4 lines touch each circle in exactly 1 spot. So again, I'm going to pause the video on the next 2. Now I'm not even going to tell you how many there are. I want you to see if you can find the total number of common tangent lines. All right, so pause your video. I'll do the same on mine. And we get back, I'll have all my lines drawn in. Okay, here we go. My next diagram in the bottom left. Hopefully you guys have 3 common tangents. And the one over the bottom right-hand corner, there was only 1 common tangent that I could draw. Okay, before I move on though, no, wait a second there, kiddos. We are in honors, as you know. That's the one thing I miss is always asking you guys what class you're in, and you guys responding, oh, he's asking that again. It's going to be a tough question. Well, here, we've had 1 common tangent, 2, 3, and 4. Is there 2 circles that you could draw that have 0 common tangents? Is that possible to draw 2 circles that have 0 common tangents? And yes, it is. Think about it. Draw it yourself if you want. What would it look like? Well, there's 1. There's 2. 2 common tangents. No, 0 common tangents on that one. All right. There's no line I could draw that intersects exactly once. Okay. So it is possible. All right. All right. Remember, a tangent line is where a line that intersects the circle in exactly one spot. Can we stop saying one spot now and actually give it a name? That one spot where it hits. What is going on there, huh? One job. That one spot where it hits is called the point of tangency. I know those mathematicians, crazy. All right, very creative. All right, so where the tangent intersects the circle is called the point of tangency. I say that because that gets us to our first theorem on tangents. A lot of theorems, warned you guys day one, a lot of theorems in this unit. If you have a line that's tangent to a circle and you draw the radius to the point of tangency, the radius drawn to the point of tangency is perpendicular to each other. Okay? The radius, if it's drawn to the point of tangency, is perpendicular to the tangent. All right? So applying this theorem now, take a look at question number 1. I have a line that appears to be tangent. C's the center. Now take a look. If C's the center, that means this line segment right here is the radius. And the radius is being drawn to the point of tangency. So by this theorem we just have, I should have a right angle there, okay? Because they're perpendicular. So now to find x, 180 degrees in every triangle. So subtract the 90, subtract the 58. You guys can do the math with me. X will be equal to 22 degrees, okay? All right, I'm going to go a lot more hands off, all right, for now anyway. Next one here. Find the value of x. So you'll see I have tangent AB. Radius CB is drawn to B, which is the point of tangency. So you guys should be making a right angle symbol there. It's perpendicular. And now it looks like I have what type of triangle? I have a right triangle. And usually when I have a right triangle and I'm doing stuff with all three sides, that tells me it's, hey, it's a little Pythagorean theorem time. Okay. The two legs are x and 8. Hypotenuse. How can you express the hypotenuse here? Because it's not x, it's not 2, it's AC. AC is the entire hypotenuse. So I'm going to represent that with x plus 2 all squared. All right, so again, a lot more on you guys doing out the algebra here. X squared plus 64 equals, again, you're ready. You're a couple months away of going to algebra 2. You shouldn't be distributing the squared. We should be doing x plus 2 times itself. So I'm pausing the video, letting you guys get to work. See if you can figure out what x is going to be equal to. Get after it. Go up and cheat. Okay, so hopefully you guys found out that after you FOIL double distributed on the right side, that you had an x squared on the left and x squared on the right. So they canceled each other out here. All right, so they canceled each other out. And now you just have an equation where you get x by itself and x equals 15. All right, let's keep trucking. Next up, all right, I got a radius. CB is drawn to the point of tangency B, so they're perpendicular, so I have a right angle here. Now, we got an issue here. I'm going to do a little Pythag, don't get me wrong. I'm doing Pythag. And I know one of the legs is x, and it looks like the hypotenuse is 10, 3 plus 7. But what about that other leg? I'm not putting a b there because I'm not having an x and a b in the same darn equation. All right, can you find that other leg, which I will highlight in yellow right now, CB? What is that other leg's length? Well, what is CB? That's a radius. We keep using these facts all unit long. If you draw any radii in the diagram, they will be congruent. There is another radii that's already drawn and it has a length of 3, meaning any other radius I draw will also have a length of 3. Okay, and now we're solving this, no factoring or anything here. X squared plus 9 equals 100. X squared equals 91. And we'll just keep it in simplest form. You cannot break down 91. I'll just give you guys a heads up there. Can't break down 91. Okay? All right, final one here using this theorem. I do have a right angle where CB and AB meet. I know AB is 12. That must mean, nope, AB is 12. CA is my hypotenuse. CB I do not know. Can we find this length of CB before I plug it into Pythagorean theorem? You're darn right I can. It's a radius. Is there another radius in this diagram? Yes. Okay. Yeah. How long is it? It's 9. So that means that radius is going to be 9. But watch what I'm going to do here. I'm going to do a little something different. I'm going to go 9 squared, and I'm going to go 12 squared. Now, instead of writing x plus 9 all squared, because there's no x on the left, that's going to cancel out like in problem number 2, you may have to factor here. And I don't think we want to factor if we don't have to. So what I'm going to do here is I'm going to call all this hypotenuse c. So c squared. And watch how I find x now. Okay? So everyone see what I did. 9 leg squared plus leg squared equals c squared, which is the hypotenuse. So let's find the length of the hypotenuse. 81 plus a buck 44 equals c squared. That'll give me 225 equals c squared. So that length is equal to 15. Now you tell me, how can I find x pretty easily? X will be equal to 15 minus 9, which is also 6. Okay? Again, could you have done x plus 9 all squared as the hypotenuse? Absolutely. You would have to FOIL, move everything over, factor probably, and reject the negative. A little bit quicker here. Okay, just finding the whole hypotenuse and then subtracting that from 9, or 9 from that. Okay? So tangent, radius drawn to a point of tangency is perpendicular. Hopefully we got that. Oh, yeah, buddy. We got a proof going now. All right, our favorite, a proof. So we got 2 tangents. Got it. We need to prove BA congruent to BC, it looks like. All right, the only way I'm going to be able to do that is if I prove the triangles congruent first. So that's where I need your help right now. Prove those triangles congruent. All right, I'll do the easy way out. BO congruent to itself. Reflexive. Okay. So what I'm going to do right now is I'm going to pause the video. And even if you can't prove the triangle's congruent, tell me some other segments that should be congruent or any other markings you can put in your diagram. Do your best and be ready to erase and write the correct work in, all right, when we're done. Okay, guys, back to business. Here's where I am right now. I knew that AO and OC were radii, and I have a theorem previously from this unit that says in a circle, all radii are congruent. Now, please make sure you have that wording in there. You need to start off by saying in a circle, all right? Because if you just say all radii are congruent, think about what you're saying. Every single radii out there are congruent, and that is false. All right, so you got to say in a circle, all radii are congruent. Got to have that beginning in there. Okay, so I did that. And now you also see my purple right angles up there at A and angle C. All right, how did I know they'll form right angles? From the first theorem we went over today, which says if a radius is drawn to a point of tangency, it's perpendicular. The theorem, though, does not say it forms right angles. And I did this on purpose. I'm waiting here for you guys to join me. The theorem says that OA and BA are perpendicular, and that OC and CB are perpendicular. It does not say they form right angles. That's not what the theorem says. So the theorem says radius drawn, and this is a little wordy, sorry, drawn to point of tangency is perpendicular to the tangent. Okay? That's what the theorem says, that the lines are perpendicular, not that they form right angles. Now, how do I get them to be right angles? Angle A and angle C are right angles. That's old school. Perpendicular lines form right angles. Okay. And now in step 6, if you want to say they're congruent, go ahead, but I know what's upcoming here and I may not need that step. So look at my diagram that's been marked up. You have two sides and an angle. The only thing I'm aware of that I've taught you guys that involves two sides and an angle is side angle side. But there's a problem. Take a look at where those right angles are. Those right angles are not in between the two congruent sides. So that is out of the question. Are they still congruent? You're darn right they are. Okay, these are right triangles. We had the fifth and final method of proving triangles congruent back in the day called the little HL. HL. All right, these two triangles are going to be congruent by HL. And before I say that they're congruent by HL, I need to say that they are right triangles. Oh, good old days. Good old days when we were all together there, right? And I was just roasting kids. Triangle AOB and triangle COB are right triangles. Right triangles have right angles. And then you guys can go ahead and finish this bad boy up. Now they're congruent. By HL. And now the take a look at those two tangent lines, AB and CB are congruent. Let it roll off the tongue, CPCTC. Okay? So hopefully you're good there. Now, what you guys just did by doing that proof, you guys have found a new theorem. Okay? We don't have to keep doing this every time. From now on, if I see a diagram like AB and CB, I can now say they're congruent by this following theorem. Tangent segments drawn to the same external, the point's got an external point because it's got to be on the outside, drawn to the same external point are congruent. Okay? Tangent segments drawn to the same external point are congruent. Basically, you got a circle, you got two tangents drawn to the same external point on the outside. Those have to be congruent. A lot of kids in the past have called this the party hat theorem. Party hat. Anybody? Party hat? Oh, it's a party. It's a party. Yep, party. Eating some chips. That's what that was going in his mouth right there. Down in some chips. Okay? Party hat theorem. But you have to write this in the reasons column. You can't write party hat theorem, even though that would be nice, right? All right, let's use that party hat theorem right now. All right. So I have a polygon that's circumscribed, which means to me it's on the outside of the circle. Find the perimeter. So add up everything we can right now. All right, add up everything we can. So here we go. Number 6. We have 4 centimeters. So now, using that theorem we just went over, two tangent segments drawn to the same external point. Both of these should be 4 now, right? Take a look, 3 centimeters. These two should be congruent because they're segments drawn to the same external point, so that should be 3. And then over here, these tangent segments should be congruent because they're drawn to the same external point. Okay, so that's how I know 4, 4, 5, 5, 3, 3. And that should end up being for a perimeter of 24 centimeters. Okay, you guys go ahead. You guys work on number 7 right now. See what you come up with. Okay, so hopefully you guys got 28 inches after you went all the way around because you had to go, all right, if this piece is 6, that's 6. Whole thing was 9, 3 and 3, 5 and 5. Okay? All right, last couple. Anything's fair game now. All right, anything we've already talked about, fair game. So we need to find X in this diagram. I'm given that angle, that central angle is $1.30. What's X? All right, well, what did we talk about first thing today? You got a radius drawn to the point of tangency. What ends up happening? I got a right angle. I got a right angle. Okay? I'm gonna put the pen down, let you guys go ahead and tackle numbers 8 and 9, and we'll get back and see how we did. Okay, so get through 8 and 9. Any circle fact can be used. All right, any circle fact for 8 and 9, get after it. Okay, so hopefully you guys remember that's a quadrilateral. It's a four-sided figure. There's 360 degrees, and I knew 3 out of the 4 angles in number 8. I knew 90, 90, and 130, so I subtracted all of those from 360 and got 50 degrees for the last one. All right, and number 9, there are no tangents, but I do remember the fact that all radii are congruent, which would make that triangle isosceles, right? And what's across from the congruent sides? Congruent angles. All right, so 180 minus the 250s ended up being 80 degrees. All right. All right. And that looks like we're good to go. Okay. So make sure you remember these new tangent theorems and get after it on the homework. All right. And we'll talk in the next meet.